Morning, everyone. Enjoying the day? Well, I know it's so early, right? Just not time to enjoy it yet, I guess. Excellent. I guess we have 3 hours to talk about memory leaks. Now, when I first put this together, I was thinking, like, okay, memory leaks, 3 hours? Seriously? But yeah, I was actually inspired by a good friend of mine, Dr. Hines. Anyone heard of Hines? Java specialist? Yeah, exactly. And he kept saying, like, hey, you should do this thing on memory leaks. And I'm going, like, why? And then he started talking about it, and I said, okay, maybe I can put something together. And then he started talking about all this stuff. And I'll get to the relevant slide, and I'll point out what Hines said and then what my response was to the whole thing. But it's actually turned out to be quite different than I expected. So I hope that you enjoy or find the talk useful, I guess, by the end of it. So I guess with that, you can ask, like, who here has suffered from a memory leak in their application? Okay, so, wow, okay, so I know everybody's arm is working. And how long does it normally take you to find these things, the source of them? How many people would say, well, we can do it this way, right? Never? That is an answer. We have customers that have never found the source of their memory leak because, they recycle of JVM and, who cares, right? Say, like, a week? Okay. An hour? 15 minutes? 5 minutes? You just discover them instantly. Okay. So we send something in between, right? So I imagine that I imagine that most people tend to find them fairly quickly, or they tend to have trouble finding them. So what we want to do here is we just want to cover, I know this says 4 hours, but that's actually wrong. So we just want to cover some of the techniques that we use to find memory leaks there, and then we'll just work through some problems here, and you can see how they're applied. So with all performance talks, we need to talk about technology. So we're going to take a look at the the technology stack that we're actually trying to do some diagnostics with today. We have tooling, so there's a couple of tools we'll dig into. Pretty much all open source, so we don't have to worry about that. I just did an evaluation of a commercial tool, which I thought was quite nice. It was pretty much the only tool that we thought we could actually run in batch mode, which offers some interesting possibilities if you are trying to do this across like a large cluster. In this case, they have probably in excess of 20, 30,000 JVMs that they'd want to do memory analysis on. So you can see how batch process might help there, unless anyone wants to volunteer to do that job manually. No, I didn't think so. Okay. And some methodology. Normally I talk about methodology, but at this level, we're sort of beyond the methodology. We're just talking about what I call recipes here. So just ways of getting through the problem effectively. So memory leak, of course, everyone knows what memory leak. It's a chronic condition which the application allocates memory that is never accessed and never freed. So that's our definition, the thing that we're actually looking for. So how does this happen? Well, okay, so when we load a JVM up into memory, it's just a process like any other process. So it has a particular memory layout. And so you can see you have different level, different places for different things, text, data, shared memory, stack, and a little bit of area for system memory. So each of these plays a particular role in the process. The part we're interested in is this section over here called C-heap, because that's where the JVM is going to start creating all of these data structures. And there's also some work that actually gets done in C-heap, and generally we call this area unmanaged memory, because it's up to the developer to just make sure that well, they're doing the allocations, but they're also freeing the memory so that the memory can actually be reused. So, yeah, so, application threads are responsible to track and free all memory locations. And, yeah, of course, this is subject to a whole class of bugs that you're probably familiar with, where your applications leak memory, either because they forget to free it, or they forget where the memory is, or something happens and, so the memory gets consumed and then eventually you run out of it. Right, so these are commonly referred to as native memory leaks. And, the symptom here is that you get the Java process is going to grow larger and larger and larger over time. And eventually, you're going to spill all RAM, and you're going to start swapping. And when you start swapping, then of course you run into the situation where your application is just going to suffer performance hits. So it's going to be running along at some level of performance, and then boom. Right, you start swapping, and you're going to get about probably a 4 to 5x hit in performance. Now, a lot of this is a funny thing. So we'll get people will email me, and they'll say, "There's something wrong with the max heap setting, because I set the max heap setting, but the JVM keeps getting bigger and bigger and bigger." And we're going like, no, okay, there's nothing wrong with max heap setting. That's perfectly fine. It works very well. It's been well tested for almost 25 years now. The problem is that you have something happening at the inside C heap that keeps growing and growing and growing. And that will cause all kinds of problems. So, yes, okay, so you can leak here. And as I say, full treatment of the subject is beyond the scope of this particular workshop, so we're not going to really cover what happens down there. Just be aware that you can leak in that area. The part we're going to actually focus on is this area known as Java Heap. And Java Heap is what's known as managed memory, right? And we can get leaks in this data structure, right? So we're going to have allocators and that are going to allocate into here. We're going to have garbage collectors going to try to clean this thing. And if there's a problem, then we can consume all of this data structure. And of course, we will run out of memory. So as I mentioned before, the mechanism in the runtime that manages this is on-demand allocation. So whenever you say like new foo, then of course you're going to allocate foo into Java Heap most of the time. And you're going to keep a reference to this, and when you drop the reference to it, then of course this stuff can actually get cleaned up. So it is the JVM that's actually helping you manage memory, and hence the term. Right. So when we're running a Java application, what I'm suggesting here is that we should monitor what's happening, not only just in Java Heap, but what's actually happening at the process level, and see if the process is actually stable in size, and if the occupancy of Java Heap remains stable over time. So let's take a look at allocations in Java Heap, just to give you an idea of what's going on here. So, so here we have some heap space, and I got it like color-coded into different words so we can sort of see what's going on. And we have a bit of code up there. And we have this other space over here. It's called perm space and metaspace. And the whole idea about perm space and metaspace is that we're going to just, when you load a class file up, the class file is going to get torn apart, and different parts of it are going to end up in different data structures. And we have to understand the structure of the data that we're loading into memory when we're allocating it. So that metadata is actually going to be loaded up into either perm space or metaspace, depends on which version of the JDK you're using, which is a good question to ask here. Is anyone using JDK 13? 12? 11? Wow, okay. 10? 9? Excellent. 8? Yeah, lots of people using 8. 7? 6? 5? 142? Well, I actually have people using 1.1.19 still. You know, they don't have the source code. It works for them. They don't care. You know, it just works really well. Okay. Anyway, so it looks like most people have moved up to JDK8, which is kind of cool. Okay, so you don't really care about perm space anymore because that went away, and they replaced it with metaspace. And so effectively, what I can say is that this metadata is going to be loaded up into metaspace, and that, like I said, is going to give you the structure of the data that's loaded into Java Heap. So if you look at the code, where is it? Yeah, up here, we can see that we have a number of allocation sites here, right? So we have a couple of implied allocation sites, and we have an explicit allocation site. So when we actually start to execute this code, what's going to happen is that we're going to create a stack frame. And of course, on the stack frame, we need to have enough space to support our allocations. And so in this case, we have, four bits of data that we need to put up there with 3 allocation sites, which means that, of course, we're only going to put primitive data into the stack frame. So which means that when we start executing the code here, we have primitive int. It's going to go into the stack. And then we're going to allocate the string here, which means I'm going to create this thing known as a primitive OOP. And of course, OOP stands for object-oriented pointer. Here's a very obscure fact. It's a holdover term from when, so this is an ordinary object pointer. I got that wrong. And this is a holdover term for when we had unordinary object pointers. With unordinary object pointers went away, mostly the unordinary object pointers were used for what's known as something called immediate directs. In other words, the runtime would have basically one bit that would say, this actually isn't a pointer to something. This is actually a primitive value, like an integer or a float or something like that. And they would just do that for runtime efficiency. Okay, so anyways, so we're going to put a primitive OOP in here, which means we need to do an allocation out into Java Heap. Right? So the question is, what does that look like? Well, that's going to depend on the data that we're actually allocating out there. In this case, is a string. So let's take a look at the string class here. Okay. So if we go down and look at the string class, we can see, okay, so whatever version of JDK I use for this one, I think it's 8. Strangely enough, the definition of string keeps changing every couple of versions. So I have a benchmark here that I could run, which runs out of memory in JDK 7, but doesn't run out of memory in JDK 8. Same data structure, right? Well, not the same data structure, same class, same code, same everything. It's just changed JDK versions, and it's just simply a change in how what the underlying data structures are for string. Okay, so anyways, so what do we have here? Okay, so we have a reference to a primitive array of byte. We have a primitive value of type int in here. Whoops, that's weird. Then we also have a static primitive value of type long. And down here, we're going to have a static reference to array of object stream fields. Does anyone know what the object stream field is used for? Shout it out. Any takers? Should have offered prizes for these, right? Sorry?
Defines serialized fields?
Yes, absolutely. Excellent. So this is for support serialization. Generally, you don't see it in the class definitions. What happens is that it gets injected in. But anyways, that's there to use support serialization. Okay. Anyways, so the point here is that, oops, where are we? We're not going to allocate memory for the statics, right? Remember, statics are defined on a class class loader basis. It's only the instance field, the instance variables that we're actually interested in. And so we're going to allocate memory for an object header. The header is going to have metadata about the object itself. So, for instance, I have this chunk of bytes in memory. So what the heck is it? I have no idea. I know that the first chunk is going to be the object header, and the first part of the object header is going to be a pointer into metaspace. And of course, the metaspace is going to tell me what the structure of the rest of the bytes are. Okay? So the object header, we have an int, we have a reference to a byte array, we have an array header, int, and then an array of bytes. So, at the end of the day, what does it all look like? This, generally. There's conditions where this might change. For instance, if you use compressed oops, then the sizes of things are actually going to change. But anyways, generally that's what it's going to look like. And you notice there's some gray bits in the coding here. The gray bits in the coding are actually, in the layout. And the gray bits in the layout are padding. And so some of the references have to be word aligned. So I can't pack the reference right up against the int because that would mean it wasn't word aligned. So what I'm going to do is pad things out so that they're word aligned. The arrays have to be word aligned. So again, we're going to pad things out so that things are padded out properly. And you can see I put the data in, so in there so that you can actually see what's going on. So like if we have a byte array, how long is a byte array? Well, how many useful bytes are in the byte array? It's 14. So that number gets stuffed up in that int value. Okay, so now we're going to allocate Fred string. And you can see we get the same type of structure here. Okay, and note, again, the object header is pointing into metaspace. Now, what I don't have properly displayed here is that metaspace is actually pointing back into this particular space here because there is a relationship between metaspace and and the data, as well as a relationship between the data and metaspace. So there's sort of these circular pointer things happening in here. Right. Now, then I have this contact thing, which is basically an ID, a name, and an email. So this is a different type of structure here. And if we put that in, we're going to see that we have the object header as expected, we have the int, and then we have two references. Okay? So again, on the stack frame, we put the primitive oop, and then we allocate this particular object. You can see it's just basically, the references are going to point back to the other bits of data. And, then we basically end up here, and we're going to leave this block of code. And of course, when we leave the block of code, all of these references, like this whole stack frame, becomes out of scope. And essentially, if we call the garbage collection after the end of the block, after we hit that curly brace, the question, this whole thing would be recoverable. In other words, the garbage collector would come along and recover all this space, right? But if we call it before we hit the end of block, then what's going to happen is that all of this stuff is still live. So if we look at a simplified view of what's going on, you can see that, okay, here's my stack frame. There's my pointers going into memory. There's my data that's allocated to memory, and of course we have my back pointers coming in from metaspace. And we get the garbage collection called. So the first thing we need to do in the garbage collection cycle is we need to do this thing called scan for roots. That's going to be the first step. So a GC root is an object that is live by definition, and it's also external to the space that we're trying to collect. So we're going to take our pointers and we're going to divide them into two different categories: internal pointers and external pointers. And so with our scan for roots, what we want to do is we want to find all of the external pointers in our system. Right? So let's take a look at our pointers here. So we have 1, 2, 3, and 4 blue pointers. These are internal. You can see the source and the destination are internal to the memory pool, right? And here we have 1, 2, 3, and 4 again, but these are the red ones and the purple ones. These are external to our memory pool, right? So if you think about what the garbage collector does when it does a scan for roots, it has to go through all of the data structures that are external to this particular memory pool and find every pointer that's pointing into this memory pool. So you can think of, I need to go through stack frames, I need to go through threads, I need to go through the code cache, I need to go through metaspace, you know, and there's a whole list of places, registers, there's all kinds of places where I'm going to have to check to try to find these pointers that are pointing into this particular memory pool. The next step, of course, is going to do the mark and sweep. And with the mark, what I'm going to do is I'm going to start with the root set, and I'm going to do this reachability test. In other words, I'm going to visit every object that I can, and as I visit it, I'm going to go into the header, and I'm going to mark it live. And then, of course, the scan is going to be find all of the things that I've marked live and do something with them, right? Or find all of the things that I haven't marked live and do something with that. So then we end up with two different garbage collector strategies in this particular case. We either end up with, I'm going to do something with all the live, or I'm going to do something with all of the things that haven't been marked live. Okay, so let's go back to this thing here, right? So we have managed leaks, commonly known as memory leak. So the data is no longer semantically useful, remains live, cannot be recovered by the garbage collector, right? Symptoms, occupancy of the heap grows over time. GC frequency and pause times will grow longer as heap occupancy grows. As you can see, the more data, live data I have in memory, the more work the garbage collector has to do. And therefore, our pause time is getting longer and longer and longer. As the live set size, the less working space we have, which means the more frequent we're going to have to clean things up. So our pause times are going to go up, and our frequency is going to increase. So you're going to have two really devastating effects at that point in time. When all of Java Heap is consumed, the JVM will terminate with an out-of-memory error. Now, technically, an out-of-memory error is thrown when I've spent 98% of recent time in a garbage collection, and I've recovered less than 2% of heap. That's when I'm going to get a GC, like an out-of-memory thrown, right? So we can actually see this with a single thread. So you get a single thread, we'll throw an out-of-memory error, and the JVM will survive. Has anyone experienced that? You have that in the back, right? That's really a fun one because it really confuses everyone because, you know, you get out a memory error, of course, your JVM exits. But in some cases what happens is that you'll have one thread that will have so much, put so much pressure on memory that it'll actually throw the out-of-memory error. And then once that thread is gone, that memory pressure is gone, which means the other threads can just, you know, work as they normally would without any issues. Right. So a common fallacy, running the garbage collector several times will free memory. Right. So as you can see, after running through how the garbage collector works, that if data is live, it's live. It doesn't really matter how many times you run the garbage collector, it's just going to be live. Now, sometimes you'll see, you'll run the garbage collector once, so you make a call to system GC with some external tool, and you'll get some recovery, and then you'll run it a second time, and you'll get some more recovery. But generally, by the time you run it the third time, you're not going to see any recovery. So what's going on in that particular case? Well, the first one is just natural recovery. The second one is going to be recovery of reference objects, because reference objects take one garbage collection to recognize that they're kaput, and then they need to be processed by something. Think of finalization as an example, right? And then at the end of finalization, then there truly are garbage, which means the second collection is the one that's actually going to free the memory. So you get that effect happening, right? And so people will think, oh, okay, if I just keep running it, I'll just keep recovering more memory. But it's generally not the case. Yeah, so they always blame the garbage collector. And it's really not the garbage collector's fault, as you're going to see. What we want to do is, first off, we want to monitor Java Heap. And so we want to answer two fundamental questions. The first one, is the heap stable over some period of time, generally a business cycle? Generally, business cycles run 7 days, but I've had business cycles run 9 days. So we'll monitor for 9 days and we'll watch what's going on. It depends on your business, right? Is the heap large enough to cope with the live data set size, right? And in particular, with the amount of work that you're asking the JVM to do, or your application to do. But also, is it large enough to deal with the allocation rate? So most people don't consider allocation rates. Does anyone have an idea of what the allocation rates are in their application? 1. Yeah, yours must be close to 0 then, right? No? Oh, right, okay. But then something like that, you're generally concerned about allocation rates because you have frame, 16.7 millisecond time budgets, and you need to worry about where the garbage collector is running and all of that. Yeah, exactly. Yeah, those are fun problems. Yeah, but most people don't actually track that, and you end up with some interesting problems because of that, right? As I mentioned before, memory leaks are going to inflate GC overheads over time. So you end up with with this particular chart here, right? So it's data set size increases or allocation rates increase, then your GC overheads are actually going to start increasing. So in terms of tooling to monitor Java Heap, there's a number of counters that you can actually get to. There's this serviceability aspect of the JVM that will actually collect this data, and you can actually get to them via JMX. So you can use some management beans, and that's the most common way to look at the data. And that can be visualized with a number of command line tools or a number of GUI tools, or people just build their own tools and use Grafana or something like that and take a look at the data. Our preferred route is actually GC logging. So if we actually want to do any serious amount of tuning on a cluster, then we're going to make sure that, oops, that's funny. Did I say Siri? Let's get this. Apple's listening in on this talk now, right? Also, so so we actually, the difference between what the data you get from serviceability as opposed to the data you get from GC logs is that you can consider GC log to actually be a journal of all the activity that happens. Whereas when you look at serviceability, what I'm doing is I'm polling for current state. So I'm just basically saying, okay, what's the state now, like every 10 seconds or so, whatever the current state is. So, the journaling means that I'm actually able to, get things that look like this, and then I can do a whole bunch of different calculations on this data that you simply can't do from the poll data. That will give you a lot of information. So in this particular case here, we're going to look at heap occupancy after the collection. And so you can see the blue is being young generational collections, the black being full GCs, with the green dots being, sort of the black line at the top being the size of heap. Actually, I think, what is this running? Parnu. Right, so this is running CMS. So the green dots are actually going to be the initial marks and remarks of it. So we're going to ask the question, is the heap stable? And the answer is yes, absolutely, right? So I'm going to draw this line and say, is the line flat? Yes, so far. All right. Is the heap large enough? Looks that way, but, who knows? Seems like it should be okay. We don't know, right? So then we look at this one here. Is the heap stable? Nope. Right? We can see that we're losing approximately 1 gigabyte of heap per day. So that's essentially what a memory looks like, right? And as I mentioned before, As the heap fills up, we get less working room, and you can see by the time we get to this end of the GC chart, things get a little messy. So that's as expected, right? So that could destabilize our application. Okay. So, quick word on benchmarking. A memory leak is a result of a bug in the application code, and it's visible if you run the correct use case. Rarely do we have timing issues with these types of benchmarks, right? You may need to worry about versions and other environmental factors, right? So when you're looking at setting up a reproducible test case for memory leak, what I'm just trying to get at, it tends to be a lot easier than some of the other performance issues that we have to worry about. In other words, we just need to be running the right use case, and it's going to be visible because this is a bug in our code. Other performance-related issues tend to be about what we call subscription rates to underlying resources, meaning that you have to get the right pressures in the right frequencies. That, you know, there's all kinds of timing issues and things like that that may be involved that allow you to reproduce things, which means that, you know, they tend to be more difficult to find. That said, there's loads of tooling grief in this space. Right. So a lot of the tools need memory to work. And if you're dealing with a large heap, the problem you're going to have is that you're just going to need a ton of memory. So I have another laptop over there that has a lot of memory on it. And just the other day I was testing a tool, and I had to load just a 30 gig heap. So not even that big by today's standards. Took me 2 hours. Right? Just 2 hours, just because of the tooling. So, you know, you have to have sometimes some patience. Tools that attach to the JVM require memory to function. So if you're trying to attach a tool to a JVM that's running out of memory, that's already running, that basically is close to running out of memory, then that's going to be problematic also. And so the heap analysis tooling needs a ton of memory. So really what we have is that we just have a lot of tools that sometimes don't work the way we would expect them to because of just the conditions that they're running in. Okay, so let's just take a little look at this funny little benchmark that we have here. It's here someplace. We'll run it. Excellent. You can see the code up there. I can't. Let's run it this way. And here. That's really fun. Did you see this? That's as far right as my mouse can go. Excellent. It's really weird. Okay. Let's see if I can just pull it this way. Nope. Oh, there we go. If I get it. Okay, so I can run it. Except for now it's over there. Okay. And not only that, because I'm boxed in, I can't actually... Okay, this is a fun failure. This is really kind of fun. No. Okay. Let me fix that. That is really weird. Let me just see what I can do about that. Yay. Okay, that seems to be working. And we seem to be, oh yeah, we're already running. Okay, here we go. So I have this wonderful little application and stuff like that. Okay, what are we supposed to do? Do some memory monitoring on it, right? Let's see what we got here. What do we have? Oh, yeah. Let's exit that and just... run it again. So I'm going to bring up some tooling here, and we'll just take a look at it this way. Visual VM, I'm sure a lot of you are familiar with that one. So I'm going to find our application. Let's see if you can guess what this does. Oops. Let's just drop off that one there. So we can just look at memory and stuff like that. So I said there's. So we're just going to have it like do stuff. And as you can see, as we do stuff, surprisingly, it just starts consuming more and more memory. I know this is really exciting, isn't it? And there we go. Exciting, exciting. Okay. Please curb your enthusiasm here. Right. And you can see as we perform a garbage collection here. Ah, there's a surprise. Nothing happened. Again, if we're looking at a GC log in this case, so I'm going to bring up our wonderful tool Sensum, which we wrote for the explicit purpose of oh, okay, I need to know where that went to, don't I? Where is it writing the GC log at? Okay, that's the wrong one. Oh, it's all the way down there. Okay, I got to dig through to find it. Okay, no worries. We'll just do that. Where did it go to? Ah, here we go. That's that one. That's this one. Okay, so now we need to go. Now I have to go through the guts of my very messy data structure thing. Sorry, I should have pulled this up, but oops, wrong one. Okay, where'd it go? There we are. Okay. Okay, so I'm going to pull out the GC log from here. And you can see there's a whole bunch of activity here. So let me just make this readable for everyone. So hopefully we won't mess things up too badly. And so you can see basically as we do a summary here, you can see we're getting this pretty much the same picture that we saw with Visual VM, right? You can see that just over time. There's the two, well, here's the system GCs that I ran. And you can see basically we're not getting any heap recovery here at all. So heap before, heap after looks the same. So this is something very typical of what you're going to see in a memory leak. We're just going to see this increasing memory like this. So yeah, that's very exciting, isn't it? Okay. And there's some other tools we can actually use to monitor memory, but let's go back to slides. That's pretty much what it looks like. Okay, I'm just going to stick on a single monitor so we don't have problems being boxed in. That's weird. Okay, so we've identified that the heap is unstable, so now what? So if we look at managed memory revisited, we see in managed memory systems considered to be leaking. The reclaim mechanism unable to free memory that will no longer be accessed, stays still alive, cannot be recovered, right? In most cases, a bug in our application codes. And we know this because, okay, with tracing collectors, which Java is a tracing collector, its tracing is precise. So anything that's not reachable there is actually going to be collected. So yeah, unused data is reachable from a GC root is what we're seeing. So we're actually looking at something that looks like this. We have reference data that's unused. And so when we basically look at the intersection of this, that's going to be our leaking memory. So that means that we're looking for a bug in our application code. So we need to find that particular bug. So this is the slide that I can attribute to Hines, because he's saying like, oh, there's so many different ways you can leak memory. And we had this nice discussion about all these ways that you can leak memory. So I put his list in here. This is Hines's slide, because I said it's really not that complicated. All I'm looking for is a chain of pointers from a GC root to a live data set size, right? And if you look at a static reference chain with all these implicit pointers, I mean, you end up with the static variable actually being a GC root, and then you have a chain down to data that you're hanging on to. Session, if anyone's using like JEE servers or whatever they call it today, it's the same thing. You stick data onto a session object and it stays there for at least 30 minutes. So I tend to call this loitering as opposed to actually a real memory leak. But of course it can eventually lead you to out-of-memory situations if you have a lot of session data. But anyways, again, GC root down to data, right? Caches are tricky. I'll talk about them later, or in a minute or so. The thread local, same thing. GC root down to data. Resource leaks. GC root down to data, but then the data tends to be connected with something like buffers in native memory. So for instance, if you zip things, does anyone here realize that zip uses native memory? A few, right? You've probably been burnt with this one then, right? Where you basically don't close the zip file and then the buffers never get returned. And eventually you just run out of native memory. And, so that's a fun one. Or file descriptors. Anyone run out of file descriptors in their process? Yeah, because you didn't close your files and then finalization didn't run for whatever reason. Yeah, so there's these types of things that can happen, right? But again, it's root down to something. Finalization bugs, same type of thing, right? Root down to something. So you look at all of these particular cases, they are root down to something. Now let's talk about caches. Caches are really fun. I've had some really fun discussions with companies, right? So I have this customer in Chicago. Every year he calls me about something or other. And the last one that was quite interesting is saying like, well, we have this application that's suffering from a memory leak. And I don't know what's going on, right? So we take a look at it and go like, oh, well, you have all this data like being collected in cache. And he said, yeah, that's just a normal part of the application behavior. And I'm going, yeah, okay. Let's take a look at the eviction policy. And so we're poking around trying to find an eviction policy, right? Can't find any eviction policy. No eviction policy. And I go like, oh, okay, well, that's a memory leak. So how do we get an eviction policy in here? Well, don't know. Go through documentation. No eviction policy in the documentation. So we say, okay, let's call the company up. They get some support. So we're talking about eviction policies with the company. And they said, oh, we have a cache here with no eviction policy. That's a memory leak. And they're going like, no, that's not a memory leak. That's normal application behavior. And go like, no, that's a memory leak. We need an eviction policy, or or this is just not going to work. So caches are confusing because people will look. They'll show up they look exactly like a memory leak, and we'll show you why a little later on. And people will look at them and say, oh, that's normal application behavior, and it's only somebody coming up from the outside who doesn't know what normal application behavior is that's going to say, no, that's actually your memory leak. So these things can get a little confusing at times. But it all breaks down to this. There exists at least one pointer chain from a GC root to the target object. And that's really all we're looking for all the time. So sometimes we can get this information indirectly. So we can use a tool called JMap with Histogram. And that'll give us pretty much a breakdown of all of the data that's in Heap, all of the live data, which is really nice. technically how this stuff works is that we're just going to ask the garbage collector threads to actually do a garbage collection, and as they do the garbage collection, it's going to collect this information and then dump it out into some form of histogram. We can use JCommand. Has anyone used JCommand yet? Some people haven't. Has anyone not used it? Yeah. It's a really nice tool if you can use it locally. And so you just do a JCommand PID and help. And it's all self-describing. And you can get a lot of diagnostic information with this particular tool. So it's very nice. Right. Anyways, the thing is, the histogram is going to show you the most prominent object in heap. And so that can sometimes be useful information. But it is still limiting. So we can go back to leaky. And so the question is, if we get a histogram of leaky, let's see what's going on. Okay, so we use JMap. Yeah, let's use JMap. Let's see what's, okay. So I'm going to use, let's make this bigger first. Everybody see that? Bigger? How's that? Okay, so let's do JCommand. So you do JCommand minus help, you can see that you can start reading it. But basically what I'd like to see is all of the processes I can connect to. So let's do a JCommand minus L. And yikes. Of course, I got a whole bunch of stuff running here. Where's the PID? Here's leaky. So that's the PID for leaky. Right? So I can do a JMap minus histo. And I'm probably just going to pipe that through more. There. And so, so it looks like the number one thing is going to be this thing here. Anyone know what that is? Yeah, it's character array, right? So if you break this down, you can see that means array, and that magic word there means character. Then we have hash map, string, and memory leaking class. Oh yeah, there we are. Memory leaking class. Just to make it clear, right? Don't you wish every memory leak was named this way? It would just make it so much easier, wouldn't it? And what are we looking for? Yeah, leaking class. There it is, right there. Arrays of object, ints, bytes, not so much. But basically, you can see that all of these guys here are really pretty much all involved with what's going on. So that can be useful right there. We can get this with JCommand. So where's the PID? I think if we just type help like that, you're going to get a list of things you can actually look for. And yeah, so we can do this. We can actually get a histogram also. So if I just replace that with that, and there you go. Oops, I forgot to put that through more. Let's just do it that way. I'm not sure why this takes so much longer. It's using the same mechanism. That's quite interesting. Anyways, what a surprise. We get the same answer. Right? So it's just two different ways of actually getting to the same bits of data. Excellent. Let's figure out what's actually going on here. The first thing I'm going to do is I want to give you like a precise diagnostic mechanism, right? This is going to give you, this will get you the leaking object with 100% accuracy very, very quickly. So I have some definitions here, which I'm going to give to you. Object age is the number of collections that an object has survived. Generation. It's objects of the same class that have the same age, right? They're going to be in the same generation. We have generational count, which is going to be the number of different generations for a given class. Okay, so there's our definitions. And now, of course, I just given you the definitions, so we have to have a test, right? So let's have a test. Here we go. As I like to tell everyone, I gave this test to my daughter when she was about 4 years old, and she passed with 100%. So that's the bar. See if we can get there, right? So I'm going to ask the question here, what is the generational count of the cross? Shout it out. 2? Excellent. Okay. What is the generational count of the cloud? 2. Okay, everybody's getting more confident here, right? Generational count of the circle? 1. The half circle, otherwise known as the half ellipse? 1. Yes, okay, that's the one that confused everyone. Star? 4. Right? What are we missing? Triangles. Excellent. Okay. Circle 1. Cross 1, 2, 1, 1, 1, and star 4, right? Okay. And that's my diagnosis. Any questions? I heard something, sort of.
Why is it not legitimate?
Why is it what?
Why is it not legitimate memory usage?
Why is it not legitimate memory usage? Okay, so I only have things in 4 ages. Generally, you know, I guess I could have extended this out to be like, 200 or 300. And you have the same pattern here. Why is it not a legitimate memory usage? Which one are we talking about? The stars, you mean?
Yes.
Okay. So if you look at the stars, they exist in all generations, which means they tend to survive all attempts to collect them. And, well, as I mentioned before, they're living in all generations, so we're creating more and more of them. If we keep that up, we will run out of memory. Okay? So that's a good question. Why is this not a legitimate memory usage? I mean, that's maybe what you want to do, but then expect an out-of-memory error. Okay. Any other questions? Generally, I get one more question. Sorry?
Let it be then.
Yes.
I don't get to 4 with stars. I don't see how it's done.
Oh, the generational count is how it's 4? Okay, that's a good question. There's stars in age 1, there's stars at age 2, there's stars at age 3, and stars at age 4. So I have 4 different generations of stars. Okay, so you think of these as the boxes of the live objects after a garbage collection at each age, broken down by age.
Right, so you count in how many boxes there are stars?
Correct.
Yeah.
Okay. Sorry if that wasn't clear.
But how could this not just be a cache with, let's say, LRU eviction policy, and then somebody just happening to be, using those?
All right. Okay. So this is a good question too. It's like, how could this not just be a cache? Okay. So if you look at the caching patterns that we generally have, we tend to have 2 caching patterns. One is I'm going to cache at application startup, and I'm not going to add anything else to that cache, and that's what I'm going to use for the duration of the application runtime, right? That's 4. The half ellipse. That's something that I cached at startup. It tends to look like that. The case that you're talking about is like, oh, well, I've just cached all the stars. Yeah, well, this tends to be the cache with the bad eviction policy, or maybe, the missing eviction policy. In other words, the cache will extend the lifetime of objects, but generally what you're going to see is that you're still going to have a limit to the number of generations that you have. If the generational count equals the number of garbage collections you have a memory leak. I don't care if it's intentional cache or not. That's a behavior that's going to eventually run you out of memory. Okay? So I think it's important spending time here because this is the part that confuses people, because especially when you talk about caching, because you're trying to hold data into memory and you want it to hang out in memory for as long as as long as needed, but no longer. It should be there for as long as needed, but no longer. And that's the key, right? So so this is what gets people into trouble, because they ignore caches because that's the way things are supposed to work. Okay. Cool. Another question. Yes? Fire away.
So you're talking about age?
Yes, I'm talking about age.
I see also that the amount of stars is increasing every age.
That's just random.
Oh, okay.
Yes. That's okay. As we like to say, we want to read into the data what's there and read everything that's there, but we don't want to go too far. So you might have gone just maybe a little bit too far, but that's okay. That's fine. It's a nice observation. Maybe I should balance it out. Okay, anyways, fantastic. You all passed. You're as good as my 4-year-old was when she was 4 years old. No longer 4 years old. For better, for worse. It's good. Okay. So memory leaks, we talked. Old is never released. New is constantly be created. Cache leaks. Objects continue to be cached, so they're not released. So it's the same as the first case. Old is never released. New is constantly being created. And in all cases, generational counts are going to be increasing over time. Right. So now we can get into a recipe, right, for triaging memory leaks. So all we need to do is profile for generational counts and just sort by generational count. That's it. It's as simple as that. Once we've figured out what we're looking for from the generational count, then we can profile for the allocation site that's responsible for creating that thing, trigger a heap dump. The heap dump, we can use a heap walker to look at all the relationships, right? And once we got all of this data, then we can just generally trace through the logic like any normal debugging step thing that you do, figure out what's gone wrong in terms of managing the life cycle of this particular data, fix it, and move on. Now, as you notice with the histogram, there's a whole bunch of things that seem to travel together. And so I like to give people a little bit of a look at what the anatomy of a leak tends to look like. Again, we got our GC root involved, and then we have some chain down into the stuff that's actually leaking. And the key point here is that we want to focus our efforts there on leaking object. The reason is, as I like to say, is that JDK classes don't leak normally. I did get caught a number of years ago at JFocus doing a demo, and it wasn't supposed to be a memory leak, but I upgraded my JVM just before going in to do the demo. I know, yeah, really stupid, dumb thing to do, and there happened to be a memory leak in that one build, which was a swing widget for the GUI I was using. So instead of actually demoing performance, I actually live demoed not fixing, but diagnosing the memory leak. Because, I showed them the GC log and I'm going like, okay, that's weird. That shouldn't be happening, but let's follow it anyways. And and we found this widget in Swing was leaking. And text box, weird things. Anyways, the point is that normally JDK classes don't leak. Something is causing them to leak, or they're along for the ride. So if you look at this thing here, that's generally going to be some sort of domain object. Now, why do I want to focus on a domain object? Well, okay, guess what leaking field tends to be? Got a guess? Strings. Exactly. Right? So if I have to find the allocation site for a particular string in my code, where is it going to be? Yeah, it's just like, yeah, okay, exactly. It's a mess. It's all like all over the place. If I'm looking for a particular domain object, what I'm going to do is I'm going to limit the number of places where I could look. I tend to limit that, in most cases, down to 1, right? In a lot of cases, we find that our domain objects are going to be created in maybe 1, maybe 2, not more than 3 places. So, that just makes it, just finding these things and being able to deal with them it's just a lot easier. But you're going to notice when we look at generational counts, all of this stuff is going to get dragged along with the leaking objects. So there'll be this pack of things traveling in the histogram together. So don't get distracted by the strings and the maps and things like that. Go for the domain object. Oops. I didn't hit the demo slide yet. Oh, here we go. Generational counts and leaky. Okay, so that's it. Let's go back over here. Is leaky still running? I don't know what that is. Script editor. And that is, that's for something else. Okay, let's, where did leaky go? Let's start leaky again then. It seems to have, here we are. Okay. Doesn't matter, let's start it again. And it's leaky, so I'll just shut it down. And run it again. And we do have Visual VM running. No, it doesn't matter, let's get it going anyways. Oops. I can type. This podium's at a weird angle. Normally your wrists, maybe as you get older, your wrists don't flex as well or something. Because Graham was doing Micronaut yesterday and he didn't seem to have trouble typing on these things. Okay. So let's get rid of this one here. Let's find leaky. Now I'm going to go to Visual VM. I'm going to do this quite intentionally because did I not restart it? I did. Where did it go to? Oh, there it is. Okay. Why is it not here? Sorry. So I'm going to go to Visual VM quite intentionally because within Visual VM there's this profiler known as JFluid. And JFluid, actually there's 2 profilers. You're going to have this sampling profiler and we're going to have this other profiler. Let's just make this big so you can see the distinction, right? But I guess the point is that the regular profiler is known as JFluid, and it's embedded into Visual VM, and it actually is the only profiler that I know of that does that properly does generational counts. So there's other profilers that claim to do generational counts, but this one actually does it the right way. So I'm just going to set up the filters in the profilers. The one thing I can say about profiling is that there's always going to be bias. A lot of the bias is set up by filtering, and you want to make sure that you understand what the bias is in your profiler, and you also want to understand what the filtering is, because there's many examples where where I can set up a profiler, just with default settings and just use it. And what will happen is that the profiler will filter the bottleneck out of the profile. That's a real win, right? Okay. Yes, the thing I'm looking for is no longer visible. Okay. So now I'm just going to attach here and get rid of that. So I'm just attaching a profiler. I know, really exciting, but you can see over on this side over here, we have this funny thing called generations, which I can just sort on. And unfortunately, unless I smack things down here, let's see. Am I going to be able to do that? Oh, that's silly. Let's just, why is that one so big? In the new version, they got rid of the little taggy thing up in the corner that said get rid of these columns, meaning that you could have fun looking. Okay, so can we see generational count? Yeah, there we go. Okay. So we can watch what's going on here. We'll go back to our leaky application and do stuff. And okay, so we do take a bit of a performance hit with this particular profiler. Did I not sort by generations? Okay, there we go. That's better. Okay. We done? Let's do it again. So even though this is a small application, the effects that we're seeing here, we tend to see them in extra large applications also. So there's really nothing different happening here in terms of profiling we wouldn't see in a much larger application. So I wouldn't worry about that. This thing is just small, so it's easier, because it really isn't. Okay, so as you can see what's happening here with the generational count, this is very typical. Most things are going to be generation 0, 1, 2, or some very small number, and then right about here, bang, we get a huge break. Okay, so our break is in this area here. And let's see if I can just make this bigger and everything like that. So I'm just going to scan through the list of things that are, so that's the anatomy of our leak. These things are pretty much all going to be involved with the leak here. And so I'm going to go for the domain class. In this case, I could go leaking field, but I think I'll go for a leaking class because that sounds more promising. Don't know why. But you can see there's a whole bunch of other things that are coming along for the ride. Generally, there's going to be some sort of collection. Here we got linked hash maps and array lists and all kinds of funky things like that. Composite data support is going to be, that looks like an MX bean type thing. So that's a management bean type thing that might be coming along for the ride. But anyways, doesn't matter. We can take a snapshot here of the whole thing. Let's just go over here. And the other thing I said we wanted was a heap dump. So let's take a look at the heap dump. So from the generational count, again, it's going back here. We recognize that in this case we're looking for a leaking class. And of course it wants to look at that. So we're looking at leaking class here. And so if we go into the snapshot here is going to be like the allocation. This is like an allocation stack trace, right? So how do we get to that particular allocation site? So let's take a look at leaking class here. And you can see that, okay, so, I have an FX GUI, and of course they have an event handler, so all of that's going to be up in here. But when I get out of the button handler stuff, you can see that I'm making a call to leaky model leak, which is then calling the constructor. So that's the init on leaking class. And of course, underlying that goes to an object init. And then, okay, so that's basically a very short path. Most of the paths are going to be longer than this, but that's the short path to the allocation site in this particular application. So we can go to leaky model leak. Okay, so we can look at leaking field, because that came along with this just to check it out. So you can see from leaky model leak in the constructor, we actually create the leaking field. Okay? Everyone got that? Excellent. Any questions, just shout them out. So we go to the heap walker here. We can go to object view. And if we go to object view, then of course we can start looking for, there we are, leaking class. So generally if we sort by size, you're going to find that the thing that you're interested in is going to be at the top. Now, with profilers, you get to see everything, right? You can't hide from the profiler. So there's some profiling artifacts that are actually showing up here. So these actually wouldn't be seen in the runtime. So this is as you can see, what they're using are phantom references in order to track the object life cycles. Okay, so we go to leaking class. There's every instance of leaking class. So we can just pick one, and we can see that, okay, here's our fields. So one of the fields is actually a class loader, and that's going to be the GC root, Java frame. So it's a GC root because it's in a stack frame. Okay. And we have this field along for the ride, also along for the ride, and our leaking field. So this is a hash map. Remember hash map showed up? Yeah. Strings showed up, always. Right? Leaking field showed up, so that's all in here. And if we want to see what's actually holding on to these things, then we can just calculate, do a calculation so that we can follow the chain of references back to the GC root. So we can just basically deconstruct everything that's happening here very quickly. Very quickly. Generational count for the, okay, yeah, we'll take a look. Yeah?
No, but can we get the generation count from the heap dump?
No. No, absolutely not. So a memory leak is a problem in dynamics. And so what you're seeing with the generational count is we're actually taking a dynamic measure, or a measure of the dynamics that's going on in a heap. A heap dump is a snapshot of what's here and now, right? So it's a static view of what's happened at some point in time. So if you have a problem in dynamics, I generally would prefer to use the dynamic counts. If I have something I can just capture statically, then I'm just going to capture it statically like this, right? And it's much easier. Now, it's not to say that you can't get, like, the thing is, like, you notice that I'm going to put load on the system when I'm doing this. The profile is going to slow things down, and sometimes I only have heap dumps because that's what customers send me. So obviously I'm going to use another technique to go over the heap dump. How are we doing for time anyways? I think we're due for a break, aren't we? Who's supposed to set the brakes? You guys?
You can choose.
Oh, I can choose. Okay, excellent. Well, I mean, I saw people were taking breaks already, so... Anyways, yeah, so we'll take a break after this one here, and then the next stage is like, if I can't get a generational count, then what am I going to do, type thing. Okay, and we'll look at another problem that's a little bit more realistic, so you can't actually tell what's leaking from the domain names. Okay, so in this case here, let's go back to the heap dump. Hopefully, yeah, it's done. So we go referent, and you can see we can just walk the chain all the way down. Now, in this case, what do we have? Oh, yeah, we don't want that one. We want this one. So that's actually an artifact of the profiling, so let's ignore that. And you can see it end up in an array list. That's the leaker. That's our leaky one, so it's a model. And that's being held in some sort of like hash map and stuff like that. So if we go to the code now, I'd expect to see these data structures actually showing up in the code. So we can actually, let's go back to the code. Where are we? This is, okay, we can kill this, I think. Terminate. Yeah, Visual VM is going to complain. So if we actually look in the code here, we can see that here's our leaky model. And our leaker is a new array list. So you can see now the profiler, as expected, is going to, here's our leak method, right? Here's our leaking class. So you can see the code is actually matching up perfectly with all the information that we dug out of the profiler, which is a big surprise, right? Oops. Yeah, so there's our structure here, our hash map, our string, our leaking field. Leaking field, really just a string. Right. the fix for this, dump it all in the trash, right? And we won't bother fixing that. Okay. Yeah, so that's pretty much it for the first bit. In the second half, what we'll do is we'll look at what happens if we can't get a generational count for whatever reason, and we'll look at a more realistic problem and try to get you to solve one in a more realistic scenario. And I think probably with that, how long's our break? 15 minutes? I can choose. Okay. I know some of you might choose a longer break than 15 minutes, but anyways, I'll look to see you back at 11 o'clock. Is that okay? Awesome. Thanks, guys. I'll take questions if you have questions also. Okay. It's 11 o'clock? Start again? Oh, look at that. Everybody came back. Wow. Okay. Where were we? Oh, yeah. Generational counts. Any questions from the first half? Half first? First? Half? No? Pretty easy. Okay. Excellent. So we found our first memory leak. Isn't that awesome? Let's see what we're going to do here now. Let's go directly into, should we go into another demo? Why not? Yeah, let's try another one here. Okay, so let's have some fun. We're going to do another application. We have set up and running here. Let's see if I can make that smaller. Let's get rid of this one. And yeah. Okay, so I have another application here. So what we're going to do is we're just going to run through the same thing and see if we can just, we'll go soup to nuts on this one, see if we can actually fix it. So I'm just going to start up this application server. So I have yeah, let's start Visual VM again. We can see what's going on here. So I can get rid of that. Bang. I don't think we need leaky anymore. So let's get rid of that. And drop this down. Okay, so let's go and... Okay, so I'm going to attach Visual VM to this so we can actually monitor memory here. And yeah, okay. So basically what I have here is I have this other tool called JMeter, Apache JMeter. Has anyone heard of this one? Maybe? A few people? Oh, just about everyone. Okay, so you're familiar with it. So for those of you who are not familiar with it, what I have is a web app here. And, excuse me. What we're going to do here is I'm going to push some load onto the web app, and we're going to monitor it to see if it has a memory leak. Anybody have a guess as to if it has a memory leak or not? Yeah, it's like, yeah, don't open the door. Right. Okay. So first thing, I have this set up for a stress test. I'm going to drop it down here so we have time to actually look at what's happening here. Let's go full tilt. Let's just blast at it. So I Visual VM. So you can get a baseline idea of what memory looks like here. And now I'm going to run excuse me, my load test here. Start up. And so we have this web app that's running. And as you can see what's running, we're consuming memory. What a surprise. And if we look at the results from here, you can get both of them here. And see I'm getting reasonably There's my response times right there for the different bits of activity. You can see that all of a sudden we have gone off in terms of response time for whatever reason. Here we go. Yeah, so that looks like a memory leak, right? So we've confirmed that we're unable to wow. Okay, that was a nice long pause, wasn't it? And we didn't get any recovery, which is quite typical, right? You get some long pauses are going to show up here. So yeah, our response times now. Imagine that, 2 seconds for loading a web page. Unreal. Locally. Let's try another one here. Anyways, you get the idea that we're leaking memory here, and it doesn't matter how often we run the garbage collector, we're going to not be able to recover memory. So the question is, what's leaking? So the easy way to do this is to actually, let's get rid of this thing here. Let's restart our application server. I'm just going to shut it down. Oh, okay, so it's already in. So the funny thing is, okay, so this doesn't actually exit with an out-of-memory error because it does recover more than 2% of heap on each collection. So one of the things, so these are actually configurable things. You can actually do this. I mean, you can go to your colleague's IDE and basically set it down to something like, I don't know, maybe you get an out-of-memory error if it doesn't collect more than 80% of heap or something like that, or 90. It's like, oh, why does my IDE keep running out of memory? So these things are. So we've actually set it on one occasion where we ran into this particular problem. Like, the application was effectively out of memory. We're spending 100% of our time in garbage collection. So let's take a look at. Ooh. That's weird. I did want to, I'm not sure what that's about. Let's get rid of that. Let's go back to this tool here. I don't know why I'm running from the IDE, but I'll just do it. So we're a desktop. So if you look at, where's our GC log? Open it up, and let's make it big. There, you can see, look, especially, actually, look at tenured. Right? So garbage, in generational spaces, a lot of the garbage collection behavior is going to be dictated by what happens in tenured space. And you can basically see we're out of memory here. Right, we're not getting any recovery here. Unfortunately, the definition is not the recovery in tenured, it's the recovery in heap. And we're still getting recovery in young generational space. And so that gives us our 2%. Yes, very helpful. What we have done in some cases, we've actually gone in and said, okay, let's take that number down to 5% because we notice we're getting like 3% recovery. So as soon as you get into this situation, like if you look at, percent time in GC, effectively by the time you get out past 200 seconds, 100% of your time is in GC. So since we fail on the 2% recovery, we can drop that number and we'll get a proper out-of-memory error, as opposed to our applications spending all of its time just doing garbage collections. So it's kind of fun. Yeah, so we'll get rid of that. Oops, I want to go back to terminals, yeah? Okay. So we shut it down, so we're going to restart. This is finished, so let's clear that out. So just so we can see what's going on, I'm going to drop this down to like, I don't know, 500. That'll slow down the rate at which we're leaking, so it'll give the tools a chance while we're running here. Okay, so let's take this. We're going to run Visual VM again. And I'm going to, attach to here. I'm going to set up the profiler, JFluid, memory settings. Yeah. So in this case, I'm looking for all classes, all arrays. Attach. Sort by generations. And let's fire up our tooling here. Okay, are we running? Yeah, we're running. Okay. So we're sorted by generational count. I'll make this big so you can watch it. Let's move stuff over here, make it smaller. Yep. Ah. Okay. Where are we in terms of the run? 92 samples. We're supposed to run 500 through. Actually, it's supposed to run for too long a time, so let's just stop that. Okay, is it stopped? Let's cut this down to 150 seconds. Okay, so let's run it again. Okay, so if we look at the generational counts here, you can see that we're getting, eventually you just get to this point where things sort of like just drop off. So we haven't run for very long. So generally I'd run for a lot longer to try to push the problem out of the noise floor. So, and in this case, we've sort of started pushing it out. So we can take a look here and see if there's anything of interest in here. Just shout it out when you see something that looks interesting. I/O, yeah. Like I said, there's all kinds of stuff in here. So this gets really kind of like anything of interest yet. So we sort of dropped from 9 to 8.
How about those tip documents?
Yeah, these. Okay, so yeah. So I probably should have given you an idea what the application does. You type in some keywords, it goes off and finds some performance tuning tips that you never want to follow. But yeah, so it lists a bunch of performance tuning tips and maybe pointers to articles where the tips came from. So it's that type of web app, right? Right. So it looks like there's some sort of tip. There's whoops. Let's grab a hold of that. Some tip document and some tips documents here that are all laying around at age 11. And there's some other stuff. We're not exactly sure what they're connected to. Thread locals and strings and all kinds of other things in there. Yeah, the point is the domain objects that we can pull out of this mess are going to be tips documents, stuff like that. Okay, so let's get a snapshot. And let's get a heap dump. And the heap dump will be automatically loaded up into here. Okay, so snapshot, we're going to look for tips. There's a tip. So sort by generation again in here. And you can see there's our tips document. Okay, so let's take a look at a tip. So yeah, so it's web app, so not surprising, there's a servlet involved here. So we have a simple query, do get. Then we go into this thing called a wildcard query. There's a tips documents, which says get tips documents. We have load tips documents. So looks like maybe that's where the IO is from. We have another overloaded load tips document with some string information. There's our tip constructor. Anybody have a guess at what it's doing? Reading a file? Yeah, likely. Could be. That'd be my guess. Sounds like a reasonable guess. Sorry? Not closing the file? Well, you know, not closing the file would lead to, I think, a different profile. But yeah, it'd be something that we'd want to check to make sure if it's opening a file and reading a file that it's actually closing the file. Although finalization will look after closing the file for us, but it's better to do it on our own if we know the life cycle. That's good. Okay, so that's the tip. There's also tips document there, so let's take a look. And you can see, you know, again, it's the same type of path, right? So there's our wildcard query. That's our tip documents get. So you know, it looks like we're pretty much in the same logical part of the application. That's our tip load, our load. And so we get a tip document. If you look at tips documents, so the tip document seems to be instantiated directly inside the wildcard query there. Make sense? Okay. So if I was taking notes here, I would probably say inside the wildcard query, we're creating this thing called a tips documents. And it looks like we're loading the tips documents by loading individual documents, or at least one. And of course, we're also looking at the tip, which seems to be involved in here someplace, somehow. Not sure how. Don't really care, okay, at this point. So let's take a look in the heap dump and see what we can dig out of here. So here's our objects. So, excellent, there's a tip, so that's easy to find. So if we sort by size, you can see that really we have a lot of these tips. We have a tip document. This is where sometimes you have to be a little careful because because there's going to be like this size cardinality thing that you're going to have to trade off here. So it might be not big, but you have tons of them. Might be big, but you don't have many. Anyways, so here's all our tips, whatever they are. So tip goes to, there's our GC root for holding onto the tip. Again, we're in this static class loader, right? So as soon as you're static, then you're going to be a GC root, pretty much. And then there's a line. Don't optimize unless necessary. Optimizing can introduce new bugs, make code harder to understand, and whatever else is being said there. So that's the data for this particular tip. That one I agree with. Don't optimize unnecessarily. Let's go back through references. Of course, we're going to have to wait here and let it compute. 25% done. And in this case, what we're going to do is we're going to get the idea of what the anatomy of this thing is, what's its structure and stuff like that. Okay, so again, we don't want to be tricked by the profiler stuff here. We can see that it's a val in a concurrent hash map. So if I open up the val in the concurrent hash map, you can see that it's in slot 1043 of this concurrent hash map. So we're in a table in a concurrent hash map. So it's a val in another concurrent hash map. So we seem to be in maps of maps. So let's open up that concurrent hash map. And so this is table. So that's a field in concurrent hash map. Oh, and here we are. We finally struck application code. So we have the static variable called all keywords in this keyword class. Can everyone see that? I need it bigger. Okay. So if I'm starting to deleave this, so that's in an object array of items, which is a vector. Wow. Okay. Who uses vector? Oh, right. And that's basically attached to a web app class loader. So that's a static element data. So it's an old version of Jetty that we're actually using here. Whoops. That got away on us. Anyways, so it's probably far enough to go. So by the time we get to application code, we're looking at the static variable, all keywords in this class called a keyword. Okay. And that appears to be a concurrent hash map. And the concurrent hash map appears to hold another concurrent hash map. Right? So we have a collection of collections, which is what I call a recipe for a memory leak. Yeah, don't do this at home. And that seems to go into something else, like into an object array. If we look at that, it's element data. So that goes into an array list. So we have a collection of collections with a static, right? Yeah, that's how you spell memory leak. Okay, fantastic. So we have a lot of information here. So we have a keyword thing where we should have like an all keywords. So let's go and take a look and what happened here. Whoop. Okay. Let's see what we have in here. Oops. Actually, you know what? I might just do it this way. I don't have it loaded up into an IDE, so forgive me. We're going to do this old school style. Desktop. JVM. Exercise 1. Source. I'll make it big, don't worry. You'll be able to see in the back. Or you can always move in the front. So we're looking for a, what is it? Oh, there's all our source code. Let's go back to our profile. What are you saying we're looking for? All keywords in keyword. Let's just open that up in something. Let's try notes. Yeah, let's try that one. That should be, hopefully we'll make it big. No, wrong one. Oops. Should not have done that in notes. Where's notepad? Where's notes? Text. Ah, there. Actually, this will be better. Okay. Right. There's our all keywords, our concurrent hash map. Okay. And so that's, and yeah, it's our concurrent hash map. Oh, look at that. It's keyed by a string, and it actually holds another concurrent hash map in there. And we can probably go through the logic here if we want to, but yeah, so here's all keywords. Yeah. So we have all keywords, so we're getting an upward, whatever an upward is, not sure. But that gives me a concurrent hash map, and I'm saying if it's null, then give me another new array list. Well, that's commented out, so that's confusing. Okay, so give me another concurrent hash map, and then what I'm going to do is I'm going to add the tip to that particular hash map. So effectively, you know, so we're just adding tips into this static collection of collections. So it's kind of like gross code. Who wrote that? Actually, I didn't. So more interestingly, what we're looking at is, let's look at the allocation stack trace. So if we look at the allocation stack trace for the tip, we do this simple query do get. So let's go back over to here. So we have all of our servlet code in here. So this is a simple query. I'm just going to make this big like this way here. So here's our do get. So it's basically based on the do get. It's some code that actually makes the call to the particular query type that we're interested in. So in this case, we're interested in a what's known as a wildcard query. Should probably just load this up into an IDE, be easier. When we look at the wildcard query, we can see, okay, here's our doValid query. So that's coming directly from here, doValid query. So the next thing we're looking at is this tips document, get tips document. So we're just going to walk through the code. Where's our get tips document? Oh, here's where, that's our allocation site here for our tips documents. And we're getting the keywords that are being passed to us from the query. So we're splitting them up and we're doing things with them. And so we're doing a get tips document right there. Okay? So we create an instance of the tips documents, and then we're basically going to iterate over all of these documents to basically add the tips into the document. Okay, fantastic. So in this case, we need to go back to the tips documents. So that's going to be in the domain, I guess, tips documents. You see, so going through this is going to be a little bit more complicated than just our simple thing here, right? But we can still see what's going on. Okay, so here's our get tips documents. So this is basically saying, if tip document is null, then load it. Okay, return the thing after we've loaded. The loaded is basically get some property, and here, oh right, here's the file stuff, right? Some who said load from file? Thumbs up, well done. You can see what's going on here. There's our read line, and do we close? Doesn't look like there's a file close in here anywhere, does there? Okay, but that doesn't seem to be causing us any grief, quite frankly. It might. Probably should put a close in, but we'll just leave it for now. Okay, so the point is that if we look at the loading, there's our tip document that we create, and then we add the doc to it, and then it's adding some information to it, and then it's setting the tips. So we're basically reading the tips from some file or whatever like that, and we're then in this document setting the tip. So it's hard to see how keyword is actually involved in all of this, right? Remember the all keywords portion of the puzzle? Yeah, okay, so it's hard to see in this code exactly how that's involved here, but we're pretty sure that it is involved somehow. And we can probably find that maybe by looking at tip document, or maybe looking at tip and see what they actually look like. But if we go back here, does anyone see anything funny with this particular piece of code? What are we attempting to do here?
There's no assignment.
Only try to load it once.
Yeah, that's what we're saying. Let's just load this once, right? So for each new instance of tip documents, we're just going to load this once. Yeah? So if we go back to the wildcard query, we're creating this tip document on every single call, which means that we're loading this thing on every single call. Okay. So that doesn't sound like something that, that doesn't sound productive. That's probably not what we want it to do here. So let's go look a little deeper here, and let's look at the tip document, because that's involved here. Okay, and so there's our array list of tips. So we've so it looks like now things are starting to get a little clearer. Hopefully, we have a collection of documents, and in each of the documents, we're going to have like a single document, and we're going to extract the tips from that document. So we're going to keep we're going to associate all of these tips with that particular document. Yeah. So it looks pretty simple, a lot simpler now. Once we start looking at the code, hopefully, code's pretty ugly. Okay, so there doesn't seem to be anything in here. This looks like a pure data holder type thing, so nothing exciting. Let's go look at tip. And, what's that? That's our keyword thing. That's a static method call. And I think the extract keywords from was actually collecting the tip and actually putting it into the all keywords data structure. Right? So we have this really weird situation here. We're basically collecting all the tips into the static data structure. And we have this seemingly unrelated behavior where we're consistently reloading the document over and over and over and over again. Right? So it's sort of like this bad mix of behavior here that's resulting in the tips actually accumulating and the documents actually accumulating and stuff like that. Okay, so we have all this stuff. So probably, whoever wrote this, possibly just a junior coder. Normally I will insult my own code because, as someone said to me once, it says, "You get paid to write bad code that doesn't perform well." I'm going, yes, that's exactly what I get paid to do. It's really fun. But I can't take credit for this code, unfortunately. This code performs badly in ways I just couldn't possibly imagine. Because the caveat that was said to me says, well, you're paid to create code that performs badly in very specific ways, which is sometimes quite tricky. Anyways, so we can generally just fix this problem by taking this stuff out of here. And, of course, we can go into the init. Okay, that's probably not all we want to do. So we want to take this part out here. And there. Are we good? Yeah. Already enough ugly comments in here. Let's take a look. So in this case, let's do that up here. Okay, so that's going to trigger the loading of the document. And since we moved it up to a field, that means we're going to have one instance per the servlet. And so once it's loaded, it's loaded. It shouldn't load again. And hopefully that, this is a kind of like a hacky fix to the overall problem, but, it at least will help us understand what's going on here. So let's just go take that and close that. We don't need these open anymore, so we'll get rid of them. That won't compile?
That gets the document returns an array or a list.
Yeah.
And you saying it will zip that.
Okay. Well, there's only one way to prove that, isn't there? Okay, is this not going to stop? Oh, it did. Okay. Hello? Anybody home? Let's get rid of that. That'll help it out. Yeah. Yeah, sometimes you got to do that. Don't do that at home either. Okay, so let's compile that. You're right. And I knew you were right. I just didn't listen to you. I should learn not to do that, or to start doing that. Okay, yeah, so let's just go here and just fix that. I knew you were right. I just didn't know why. I'm blaming it on jet lag. Can I just blame that on jet lag? Okay, thank you. Yeah, jet lag's fun. Love it. Who here enjoys jet lag? I don't know why I'm formatting that. Oops. Still not right. Okay, because I'm just doing this the stupid way. Okay, there you go. Now it'll compile. Are you all happy? I know you can't read that, right? How's that? Did I make any? What other mistakes did we make here? Excellent. Okay, let's try that. Oh, we have an IO exception in there. Of course, if I was using a real ID, it would have told me that, right? Okay, so let's just... There. Don't do that at home either. Closing brace. Did I miss the closing brace? Don't tell me that. Okay, how many mistakes can I make here? What happened? Something. Okay. That was weird. Servlet. Yeah, how many mistakes can I make? The code was small, so you couldn't read it. How could you possibly know there was a mistake in there? No, it's... Ah. Yes, got me. Okay. There. That's fine. It just looks weird because I'm ignoring formatting rules, right? There. How's that? Is that better? That'll compile. Yes. Okay. And let's all test out. Anybody fairly confident this is going to work now? Okay, let's just bring up Visual VM again. And we'll just attach it. Yeah, that one. Let's get rid of that. That and that. So we're just focusing on memory. And we can come back here and, okay, we can blast this now. Let's have some fun with it. Okay, let's go. Where did Visual VM go? And to everyone's surprise, I think we can declare victory. Yes. Victory. Well done. Okay. So that's pretty much the whole shebang. Generally it goes faster, especially if you start using IDEs to traverse through code. But we wouldn't want to do that. Okay, so this is a more normal memory pattern. We could check the GC log. We're going to see everything is kind of fun, but I think we've killed this one. Any questions? Pretty simple? Yeah, that's the way it's supposed to be. Simple. That's the whole point is to try to take these really hard problems and apply tools and techniques to try to make it as simple as possible, because when you get into larger environments, there's so much noise there and so many other things going on that you can very easily get confused as to what's really happening. So we want to try to simplify as much as possible. Okay, let's go back to here. And let's go on to the next fun bit. Okay, so as you probably noticed, as we're profiling things, our applications slowed down considerably. And so, you know, some of this memory profiling, people don't really consider it suitable for production environments. I might argue with them, but, you know, it's their production environment, so they can decide what to do. Also, maybe difficult to use in test. Memory profiling distorts the allocators. This is really a fun thing. Does anyone know about escape analysis? 1, 2, 3, 4. Okay, not too many. Okay, so escape analysis is a test that's applied to your allocators. So I'm going to say, like new foo, the runtime is going to look at that and say, can this allocation, can this data escape so that it's visible to more than one thread? Right? And there's different types of escape. So you can have a full escape, which means, this data can be seen by multiple threads. You can have what's known as a method escape, which means I'm going to make a call to something else, and I'm going to use this particular, piece of data as this object is going to be a parameter to that particular call. And maybe I have no escape, which means I can say that, this is definitely locally scoped. It's, only this thread is ever going to see this particular piece of data. Now, the reason why this is important is because I can apply different allocation strategies to each situation. If I know it's only local, it's quite possible I can just unbox the whole thing, do a scalar allocation of all of the data, and it ends up on stack, or maybe it just ends up allocated in registers. Point is, it never gets into heap. So we avoid the heap allocation altogether. So we can actually do things like that. Now, what I'm going to do is I'm going to put a profiler in there, and the profiler is going to do some bytecode injection, and it's going to basically say, I want to track this particular object. And as soon as it's done that, we have more than one thread looking at this particular object. Actually, we have more than one thread looking at every single piece of data in your system. Guess what happened to escape analysis? It just got blown away, right? Everything is going to escape, which means I have to do a full-blown allocation of everything, where before I might have been able to even eliminate the call site so that there was no allocation occurring whatsoever. So the memory profiling actually distorts the allocations in the runtime. And that's going to cause all kinds of, can potentially cause all kinds of difficulties. Fortunately, it doesn't really affect us with memory leaks, but for other types of profiling, it can. Because of that, these things might not be suitable for running in production environments, because they really mess up a whole bunch of things that are happening for you naturally. Alternative technique is to take a heap dump, or take a snapshot of the heap, and then do a static analysis of the heap dump. Now, as I mentioned before, this is very memory intensive. It can take, so for my testing, I was looking at a 30 gig heap. I had to set the max heap size to 48 gigs in order to be able to effectively do that analysis, right? How many people here have like 64 gigs of memory on their machine available to them? Yes. Proudly put your hands up. That's 1, 2, 3, 4, 5, 6, right? Notice my hand is not going up. I suppose I could get one if I asked the right people, but and it's really funny. Actually, it's in the springtime I got a call out to this customer, and they said, "Well, we think we have a memory leak because we're getting out of memory errors." Right? Surprisingly, generally when people say, we're getting out of memory errors. They're getting out of memory errors, right? And, you know, in this case, they actually weren't getting out of memory errors. There was something else weird happening. It was a really weird thing. Their vendor had recommended that they make a call to system GC every 2 minutes. Okay, I like that people are laughing at that one. That's a great sign, because everyone was trying to figure out why this was not a good idea. So you know, why is this not a good idea? Well, they had this like sort of pseudo microservice type architecture, and actually we built some models to actually look at. That's a bit of an aside, right? But we were looking at models to actually predict how much latency would be added to each request in a microservice architecture based just on the GC pause time characteristics of your application. So we can actually do that. That's quite a nice calculation. There's a couple of different ways you do it. We did this. I just did this for a client like 2 weeks ago. We came up with the understanding that there was a 99.99999 whatever percent probability that they're going to be hit with about a 200 millisecond pause time, at least one, right? And then when you start going to 2 and 3 and 4, then of course that gets closer to 100. Yeah. Anyways, so what was happening is that the GC pauses were actually caused by the system GCs were actually causing calls between VMs in the cluster to actually fail, and they weren't being managed. The failures weren't being managed properly by the product, meaning they just like fail silently. And so they were wondering why this whole thing was taking so long. Anyways, the point is that they thought they had a memory leak, and then they're looking at it saying, oh well, we have these really large heaps because they're like 64 gigs, and that's another funny story. Since the vendor actually thought they had a memory leak, also they kept telling them just to get bigger and bigger machines, and with more memory. When I looked at it, they're actually using 2 gigs of memory. Anyways, yeah, it's when things really go off, right? Anyways, so here's the other funny part of the story. The original story is like, I thought, because who gets this wrong, right? When you get out of memory error, who gets that wrong? So I said, okay, and you have large heaps. I said, I'm going to need a machine with about 64 gigs of RAM on it in order to do a proper analysis. And the guy says, eventually comes back and says, well, we couldn't actually get you a 64 gig machine. We got you a 16 gig machine, but it has a really fast CPU on it. I'm going like, yeah, okay, thanks for that. It's really going to help. Yeah, so if you need memory, you just need memory. If you guys have the 64 gig machines on it, I guess you don't care what type of processor you have. You have memory. I'm in awe. Because that's what you actually need to do this type of work. Okay, so the idea here is what we're looking for looking for these things called dominators, and maybe some of you have heard of this term before. And we're particularly looking for dominator trees. In other words, what I'm looking for is this idea of having a single path or a very narrow path to what's known as a large retained set size. And so I'm going to define a retained set size basically saying, like, if I have a node in a graph, what is the size of all of the things that this node points to? Okay? And that would be the retained set. So we're looking at the size of the retained set. Okay, so if we look at this thing here, we have a dominator object. So this is any object in an object graph that must be passed through to reach any other object, right? And this can actually become a pinch point in the object graph. So you can think of an object graph of all these pointers wildly going off in different directions. If you end up with something that looks like that, then you can see basically our dominator object is going to be the red one. Right? That's going to be our direct dominator. We can also have our immediate dominator. We can also have non-immediate dominators, which are going to be the green dots. And of course, anything falling from the red dot is going to be these black dots, which are the ones we're going to be concerned about. That's going to be our dominator tree. So it's the red thing with the black dots. Right? In this case, the gray object may or may not be included. It depends on the tooling's definition of what a dominator tree is, or if it considers that to be part of the retained set or not. Okay? Now, I guess you can see that this looks suspiciously like a cache, right? Because typically with a cache, you're going to have like this very narrow thing that actually has a large retained set size. So again, caches get confusing here. That's all you have to do. Okay. So the memory leak triage in this particular case is a little simpler. We don't have to worry about generations and generational counts and things like that. All we're going to do is we're going to acquire a heap dump. And we can do that very nicely using these flags on the command line that says, like, if I get an out of memory error, then dump heap for me to whatever path that we specify. Or we can use some tooling, like Visual VM or JCommand, to actually generate the heap dump for us. And then we need some tool that's going to calculate the dominator trees for us. And then it's just basically, let's inspect the dominator trees to see which ones are actually leaks and which ones are actually caches that are functioning correctly, as opposed to caches that are actually leaking. Right. So there's the warning there, right? Heap dump is a snapshot, which is a static view of a problem that is a problem of dynamics. A cache is often a candidate leak, and people tend to ignore it, even if it is the leak. And that's in bold and probably should be repeated and flashing. Right? So, so the message is there, don't be tricked. Right. So we can do dominator trees in leaky. So that should be exciting, right? Because I just closed leaky. Let's try. Yeah. Okay. Let's start up. I'm going to say let's try. Let's have some real fun. Let's close this. Did I get rid of that? Yeah, I did. Let's go back to the wildcard query. And let's see. I'm much better at putting bugs into applications than taking them out. Than taking them out. So in this case, what I'm going to do is I'm going to just put the bug back into the application. So that should compile first time. Equals, what does it say? New tips. It's there. So let's get rid of this. So I'd say one of the things that we do quite frequently thought I got rid of that too. Okay, doesn't matter. Okay, so we're good to go. Anybody have any complaints? So I've reintroduced the memory leak here into the problem. So let's just go and compile that. So one of the things we do quite regularly is we'll just take known problems and we'll test tools against known problems just to see how the tools actually expose the problem, if they expose it in a useful way that's easy to sort out, to sort out what's going on if you didn't know what the problem actually was. So generally, I mean, if you know what the problem is and it's hard to find in the tool, when you don't know what the problem is, it's going to, you're going to just have that difficulty to overcome. Okay, so let's go back to JMeter. Sweeper out. Let's just run it quickly. I'll let it run for a sec. I'll just let it run till full. Anybody got any questions so far? This is simpler, I think. How many did we say? 1,500? Maybe we don't want it to go that far. Yeah, it's already starting to have fun. Let's just stop it at about 400 or so. Benching is so much fun. So I work at home, and whenever I'm benching, my wife will come into my office and say, "What are you doing?" And no matter what I'm doing, if I don't want to be doing what she wants me to be doing, I always say benching. Because she'll look at it and say, "No, you're sitting around doing nothing." I said, "No, I have to watch this very closely." It's really good. Works every time. Okay, right, so let's go out here. We're going to do a J command minus L. And let's make that bigger so you can be as confused as I am. So that's the one we're looking for. So I said before that you can do a J command, command and that, and you can type in help, and as I said before, it gives you a list of all of the things that you can actually do. You can get help on each of these different things. So in this case, I'm just going to so I'm just going to say, okay, let's do a heap dump. Whoops. Sorry, that's not what I want to do. Oh, that's fun. Yeah, I'll get it eventually. Okay, so now heap dot was it? I'll just call it that. We'll deal with it. Okay, so now we're going to dump heap. And man, that's taken a while, isn't it? So I'm going to launch this other tool, which is known as a memory analyzing tool. Should have started. Where'd it go? Yeah, here it is. Okay. So MAT is an Eclipse-based tool. Maybe you've seen this before. So what we can actually do is I can open a heap dump. And, oh, that's fun. It's right here. All known formats, all files. There we go. And there it is. We can load that. Is it done? Yes. Okay. So we're going to load it up into the tooling. And it's going to take a while. So at this point, instead of doing nothing and saying that I'm benchmarking, I can actually take questions on this. Then you can see there's our little progress bar in this time. So what it's basically doing is it's loading this data and it's going to parse it. It's a good thing I didn't let it go bigger, I guess.
Well, it can handle files that are bigger than...
You're right. What it does is it creates a lot of index files. So the comment was it can handle files that are larger than memory. So yes, because it as it's parsing the file, it creates a lot of index files. It sort of like makes a quote-unquote database. So just for fun, what I did was I started a project which I haven't had enough time to actually work on, which I call JHeapo, which is actually loading the heap dump into Neo4j. I don't know if any of you are familiar with Neo4j. It's a graph database. And the reason why I wanted to use Neo4j was twofold. One, I was looking at getting the larger than memory scalability issue solved by Neo4j, not having to come up with that solution myself. And two, what I didn't show you is that the heap dump, well, in MAT, they have this thing called object query language, and actually in Visual VM, the Heap Walker, they also have object query language, which are slightly different versions of the same thing, which is an odd mix of SQL and JavaScript. So if you can think of anything stranger to mix, then that would, I don't know what they are, but that would work. Okay. And so you can actually do some interesting things with the thing. So one of the things I actually did before was like cut data or figure out how to cut data out of the heap dump so that we could put it into its own file and like deserialize it. It was like a large array that was serialized. Other thing is the odd one was a customer sent me a heap dump, says, we have this query, here's the results, but we have no idea, we don't know what the actual SQL was. Can you like match it up? And which is kind of fun because I found the data, found the results set, and of course attached to the results set is the query, right? So using OQL is able to like work backwards and figure out what the actual SQL query was and gave it to them, which is kind of fun. Okay, so anyways, so it's actually ingested the file now, so I can stop with the boring stories and get forward. So we go to the leak suspect report, and let's just see what it tells us. It's actually now calculating what's known as suspected leaks. So what you can see here is that we're actually going to find that the tip is leaking here, and it's going to give you all of the information that we got before about what was happening with tip. And but what we're going to miss is the allocation stack traces. Okay, so we're going to have less of a clue as to how to debug the code, but we're still going to find the leak. So as we go through this here, you can see class loader component tips occupies 99.6 of all live data accumulated in one instance of this hash map keywords, right? So basically, it's given us a lot of the information that we fettered out by looking at the heap dump using the heap walker. It did it automatically for us, which is really, really nice. But as I said before, now we have to go through the code, sort out the logic. In this case, the logic is kind of broken because the leak is happening over here, and the code that's actually causing it is over here, and there's a very narrow link between the two. So that can get a bit tricky. Anyways, now in version 7 of Flight Recorder, has anyone been using Flight Recorder? Right. So in version 7, which is not out yet. Yeah, exactly. What you're going to see is that you're going to get this type of information that you're seeing in MAT. I won't run it right here yet because I haven't built the latest version of 7. Sorry?
You can download it.
It's not included in the JDK anymore.
But you can download it from JDK.
Yes, not version 7.
7 of the ones now.
Okay. So I've been told you can download it from OpenJDK, which I should know because our team has been instrumental in putting OpenJDK together. Actually, yes, but that's the other thing is that what you actually download are the plugins. It's not bundled. Okay, I'm gonna look at this one because I looked at this on Friday, and it's still plugins for Eclipse.
Because I did it wrong.
Okay, I'm being told I'm wrong here. Okay, which is okay. That's good. Anyways, the point is you actually did this with Marcus?
Yeah.
I'm sure he's using plugins. Anyways, you can either get from GitHub the project, you can build it, and then you can plug it in, load it as a plugin to Eclipse. Point is that the latest version is going to give you the allocation stack trace along with the information that you're seeing here with MAT. So I would say that as soon as 7 is released and you're able to use it, or if you want to use pre-releases, that it's going to give you a lot of information here that Flight Recorder currently doesn't give you. Excuse me. Right. So it gets that information fairly cheaply. Okay. Anyways, so we've got the same information here. Okay. So any questions on that? It's pretty simple. So just to finish up here, I'm just going to go a little bit over class loader leaks. So I think I've mentioned a lot of this stuff before, so I'm not really going to go over it again. But effectively, with a class loader leak, what we're seeing is that the same classes are being loaded into metaspace, and for whatever reason, they're not being released, which means you're not actually able to garbage collect them. And what we have to do in this case is we're trying to figure out, okay, what is the linkage again to a GC root that's actually not allowing the class definitions to be garbage collected out of metaspace. Now, in perm space, it used to be that you could, when you unloaded a single class and there was no more instances of that class left in memory, that single definition would be garbage collected. In metaspace, that's not the case anymore. What's going to happen is that class loader is going to get a meta chunk out of metaspace, and everything the class loader loads is going to go into that meta chunk, and that meta chunk is going to be garbage collected in one shot. We either get the whole thing or we get nothing. Okay? So if there's a single reference live, then the whole meta chunk is going to stay live. So we don't get this granularity of garbage collection that we had with perm space. So if we look at it, okay, so how is this all working? So to help understand it, let's review class loaders. So we have started off with this pseudo class loader called the bootstrap class loader. The bootstrap class loader loads things from the JRE /lib directory. So anything that's there will get loaded up into the bootstrap class loader. We have an extension class loader which comes from JRE extensions. So if you drop jar files there, then they will be picked up and put into this extension class loader. Then we have the system class loader, which takes things from the class path. Now, we all use application servers or different types of applications, and they tend to have their own classes, and they tend to load their own classes into their own custom class loaders. Now, this is where the whole world gets really murky, is because the custom class loaders tend not to follow the rules that the other class loaders follow, that the system class loaders and the extension class loaders, bootstrap class loaders follow. And that is that if I have if I make a reference to class foo, then what I'm going to do is I'm going to start typically at the system class loader. I'm going to say, I'm going to start at the system class loader, and what it's going to do is ask its parent, okay, do you have a reference to foo? And of course, then the extension is going to delegate to the bootstrap and say, do you have a reference of foo? Bootstrap doesn't have a parent, so it's going to answer no. Extension will answer no, and the system will say, okay, fine, I have the definition, and so that's the definition of foo that I'm actually going to use. Okay? So if you look at systems like OSGI or JEE, where there's no class loading spec associated with it, they tend not to use a delegating model. In other words, what happens is that they'll say, do I have it? Yes. Okay, I'm going to use that definition. I'm not going to delegate up. And that can get you into some really interesting situations. So have you ever been in the situation where you're say something like, A equals new foo, and then you go like B equals new foo, and you say, does A equal B? And you get a class cast exception? Right? Yeah, okay. This is like this weird thing happening, right? Because you have different class loaders that actually have the same definition, and because the class loader and the class form the identity, then that's an indication that basically somebody has messed up in terms of where they've picked the definition up for that particular class, and you have multiple definitions in the system. So that's one of the issues that can happen. There's some other issues that can happen, just particularly when you come into application servers that like to reload things, right? So I'll take the war file or EAR or jar or whatever out of the deployment directory. I'll drop a new one in, and then what's supposed to happen is that we're going to get rid of the old class loader with all the definitions in it, and then we'll bring up a new class loader, and we'll reload that whatever deployment entity into the new class loader. And of course, the old stuff is actually supposed to go away, and it doesn't. And the question is why? Well, the answer is that I still have some definition in there, and this definition is actually there's some definition that's still through some route is hooked up to a GC root. And because we're still hooked up to this GC root, we're just not able to unload that class or that set of classes, particularly the class loader. Okay, so anyways, this is a little bit more about, what did I miss here? Yeah, so with modularity, the extension class loader is now the platform class loader. The system class loader is the default class loader for modules not included in the JDK, right? So it's also referred to as the application class loader. So it's no longer what's known as the URL class loader, which was the old system class loader. So anyways, there's been some changes in class loading that are there just to support modularity. And we're still sorting out, what new memory leaks are in there because of this type of change. But anyways, the point is that you get into some really interesting situations here. Static variables are always considered live as long as the class loader is live. Implies static variables will be considered GC root. Implies any object attached to these static will be considered live. That live will actually keep the metadata live. When you have the metadata being live, then of course, that whole meta chunk is no longer going to be collected. So we have this code smell, which is like statically scoped collections, which is always, to me, something that's, spells memory leak. Can I just go with a slight aside here with this class loader thread thing? So generally, most people will take the second form when you're actually dynamically loading a class. You say class for name, string name. And what I've always suggested is that form of loading classes should be deprecated, right? You should always favor the first version. And in the first version, you're actually going to name the class loader. And typically what you're going to do is you're going to ask the thread to get the context class loader, so that when you actually load these classes, you can set the context, the thread, sort of the context class loader for this particular thread. Or you can just basically specify it in the class for name. And so this way that you know exactly where things are coming from. So that helps avoid this class cast exception problem by being explicit as to which class loader you're actually getting the definitions from. Anyways, you look at something like this, right? This is typically what you end up with in terms of a leak. So if we were to actually snip the reference between system and an application in terms of the class loaders, you would expect to see all of the red stuff garbage collected. But in this case here, I have an inner class which implements an interface which extends an interface which is held, which has been loaded by the bootstrap class loader. You can see this external chain here. So what happens is when I get rid of the class loader by disconnecting it, right, like nulling out or basically throwing it away, I still have this reference chain back to the bootstrap class loader, which means none of this can be garbage collected. So the question is, how do you find these things? With perm space, it was easy because perm space would come with a heap dump, and then you could use all of the regular tools you had to find the reference chains that you needed. With metaspace, unfortunately, well, perm space was never part of heap, but it looked like Java heap, so you could easily get it into the heap dump. Metaspace is a completely different data structure. It's a C++ data structure. It's different. It doesn't come with the heap dump. You can't trace into it, unfortunately. So we sort of lost that ability. So we have to use different techniques now to try to figure out what's going on. Now, so a little bit about metaspace is size is uncapped, meaning that if I'm leaking metaspace, this space is just going to get bigger and bigger and bigger and bigger until basically the VM gets big enough that it is bigger than the amount of RAM we have, which means we start swapping, which means you're going to get performance hit all in one shot. Eventually, it'll grow big enough that you'll run out of physical, just the operating system will run out of memory, and of course, the process will fail at that point. Now, you can cap the size of metaspace, and we recommend doing that so that you actually get a normal failure before things go really bad. Yeah. All right. Right, when the threshold is reached, the JVM will fail with an out-of-memory error. It'll say metaspace full, then you know that you have this type of leak. So in terms of getting a handle on what your class loaders, the situation is with your class loaders, we can use this JMap perm stat. And you can see right here, what it's going to do is it's going to list all of the class loaders that are live in our system. Or all the class loaders that are in the system, so then you can sort through and try to figure out which ones shouldn't be there, and that should give you some hints as to what is actually leaking. So the recipe in this case is like load, exercise the application, unload the application, and then run the garbage collector a couple of times, because there's lots of reference objects used in here to hold things together. And the reference objects are used intentionally because they need to set up these relationships, but they don't want them to be strong relationships because they want them to be able to go away, as we unload things. So basically trigger the garbage collector at least twice so you can deal with the references, and then what you want to do is start looking for things that shouldn't actually be there after you've unloaded the application. If there's things that are there after you've unloaded the application, then that's going to be the source of things like sources of routes between the metadata and a GC route, which means that the meta chunks that make up metaspace are not going to be able to be collected. At that point, it's debug to try to figure out, okay, what's the life cycle here? Why is that chain not being broken when the life cycle came to its natural end? Now, for some things, we can use native memory tracking to figure out what's going on. I don't really cover native memory tracking in this particular talk. But suffice it to say that by the time we get into JDK8, what we can actually do is we can track the JVM's use of native memory in certain cases. So things like zip is not tracked. So if you use like native buffers for zip files, that's not tracked. But there's many other things that are actually tracked. So if we turn on native memory tracking, what you can do is you can actually start understanding the native memory use of your application by the things that are actually tracked internally. Okay. So with that, I'm going to end this lengthy workshop on memory leaks and just take questions from here until time runs down. Or you leave, whatever comes first. Oh, please do go out and rate the session and And that I've been asked to just say, please go out and rate the session. So please go out and rate it. Whether you liked it or found it useful or not. I guess if you didn't find it useful, you would have left by now. So that's okay. So any questions now? Yes, sir.
How big can this metaspace problem actually be? Because,
Metaspace can grow to the amount of physical RAM you have on the system and beyond.
because you kind of would expect that once all classes are loaded, there's nothing.
You should expect that once all classes are loaded, that nothing else should be happening, and that's true. That's exactly what will happen. But if you're in a situation where you're loading or unloading things constantly, okay, so maybe you're synthetically generating methods like Scala does, or Ruby, JRuby, or these types of things, where you're just collecting, and somehow they're not getting unloaded after they're being used, then, of course, that's a situation where you can continue to grow. That's one situation. But if you're unloading or loading full applications in a JVM that's running for a long time, then that's another situation where you can see this happening. Okay? Mostly these are going to happen in test environments. In production environments, they tend to be, you don't tend to see that behavior as often. Any other questions? Yes, sir.
About the class loading leakage.
Yes.
If you have a problem there, well, you can check if you have it, but can you also fix it?
Okay, so you can check and diagnose it, and the question is, can you fix it? Yes, and it might be that you've run into a bug inside JDK classes, at which point you'd probably be interested in, they'd be interested in having you submit a patch to fix the problem, or at least file a bug and say, this is what I think is needed to fix it. But in many cases, you can find that there's some application logic that you can fiddle with that will actually solve the problem for you. Okay. Any other questions? Okay. Well, yeah, sure.
The generation count.
Yes.
You get from Visual VM.
Yes.
But can you also get it from the command line tools, like JCommand?
Right. So the generational count, can you get it from? You can get it from Visual VM, and that's the only tool that accurately reports what a generational count is. Your kit and some of the other commercial tools will estimate a generational count based on snapshot analysis. So they'll look at snapshots, and so they'll give you an estimate of a generational count.
You can't get it from the command line tools.
You cannot get it from command line tools. No, absolutely not. Okay.
In production, you may have a problem not be able to use Visual VM.
So yes, so in production, you may not be able to use Visual VM. That's quite correct. So the technique that they actually use to collect generational counts is quite simple. They're going to use an phantom reference. And so when you create the object, you can wrap it in a phantom reference. And then what you do is you track the number of garbage collections from the garbage collection MX beans that are attached to the platform M bean. And at that time, and then basically you can, as the phantom reference is being processed after it's been released, then you can just do a diff, right? Or you can, if you keep the phantom references, then you can do a diff amongst, like if you have a collection of phantom references, you can just go across the collection and just get that information at that point in time. So it's possible you could write something like this on your own that's production friendly. We've done that in the past. So what we'll do is we won't look at everything. We'll just look at some things. So I might not look at JDK class. I don't care to be instrumenting string, for example. And what that does is it tends to take a lot of pressure off of the runtime. As we say about profiling and sampling, the one thing you want is you want your sampling to be completely randomized, right? If it's not completely randomized, then you can have a bias in the sampling, and the bias in the sampling will give you a bias in the profile. In this case, you can bias the profile in a way that's good for you, but you still want it to be randomized. Okay, so you can bias it away from JDK classes, Hopefully, the JDK classes aren't too involved. So it's just business classes that you'd be wrapping, but I'd want to sample, and I'd want the sampling to be randomized, certainly not regularized, right? So I wouldn't go every 5th allocation or something like that. You'd do something that would say, I'm going to just randomly select some allocation and wrap it and monitor it. And in that case, you should be able to get the leaking object relatively cheaply.
That also involves code changes?
Well, you'd have to, so what we've done in the past, we'll just write our own agent that will instrument the code. So in this case, you're going to instrument the allocation site, right? So you can do some inspection of what's, and that's, we'll just do the instrument the allocation site, and so basically, you as part of the inspection, you'll just decide, do I want to track this or not? So you can generally do that fairly quickly. So there will be some hit, but you can generally minimize that.
And it's only temporarily.
Yes. And if you have a cluster, it's only one VM in your entire cluster. So it shouldn't be that bad. Okay? Thanks.